Alright, so once again we have this box sliding down a ramp, and the forces on the box are the weight, a friction force tangent to the ramp, and a normal force perpendicular to the ramp that keeps the box from falling through the ramp. So again, we'd like to do a vector decomposition, but this time we'd like the vector decomposition to be in terms of these basis vectors, e hat 1 and e hat 2, that are aligned with the ramp. E hat 1 is tangent to the ramp or parallel to the ramp, e hat 2 perpendicular. And once again, we will let the scalars W, F, and N represent the magnitudes of the weight, the friction force, and the normal force, respectively. So this time I'm going to start with the normal force. Let's put that down. And the normal force is perpendicular to the ramp. Notice that the E hat 2 direction is also perpendicular to the ramp. So therefore I can write the normal force simply as N in the E hat 2 direction, right? There's no component of this normal force in the E hat 1, so that's it. Now the friction force is almost as easy. Take the friction force. This is all tangent to the ramp. Tangent to the ramp means E hat 1, right? So I've got F E hat 1. And of course I got to be careful because my friction force, at least as I've drawn it, is up and to the left, whereas positive E hat 1 is down and to the right. So they're the opposite directions. So since F is a magnitude of that force, a positive scalar, I should put a minus sign right there to indicate the direction of the friction force being up and to the left when my scalar F is positive. And now that one's done. Now finally let's consider the weight vector. So we'll call that W, and let's go back to our recipe. The recipe, step number 1, says draw a vector triangle. So the vector W is straight down, right? So let's do that one first. Now remember, this weight W is going to be the hypotenuse of our triangle. The other two sides of the triangle are going to be tangent, or I should say parallel, to the E hat 1 and E hat 2 directions. So in the E hat 1 direction, I've got something that looks like about this way maybe. I'm trying to draw this vector tangent or parallel to that one. And then the piece in the E hat 2 direction would be like this. And there's my vector triangle, right? W is the hypotenuse. The other two sides are parallel to the E hat 1 and E hat 2 directions. Again, I could have done the E hat 2 first. It would have been this way, and then E hat 1 that way. It doesn't matter. So let's move on to step number 2. Step number 2 is to identify a key angle. Going back, there is this angle theta that's defined in our problem. Can we identify any of these angles with that angle theta? It's not obvious, at least to my eyeballs. But if you think about how the geometry works, how these lines are constructed, I'm hoping you can kind of see it. And the best way I can illustrate it is with this little tool over here again. So here's my weight vector. In black, it's vertically straight down. The E hat 1 direction, there's the red one. The E hat 2 direction, there's the blue one over here. Now, theta is the angle that the red one makes to the horizontal, right? So what if I were to switch that? So sometimes it's easier to see that in some sort of extreme. So here's more or less what we get for the angle theta that's shown. What happens if I make theta small, make this ramp not so steep? Well, in that case, the red curve is going to get more horizontal, right? What do we say? That was this way, right? So if I make theta small, it looks like this. So the angle in our vector triangle that's getting small is this one right here, right? This one right here. If I make the angle, if I make the ramp shallow, then this angle right here in my forest triangle gets small. If I make the angle steep, that is where, if I make theta pretty big, close to 90 degrees, whoa, look what happens. Then this angle again down here gets close to 90 degrees, right? You can even get it closer to 90 degrees. There it is, right? So it seems like this angle down here is the one that's corresponding to the angle of the ramp. So tentatively, let me just say that this one, let's say that one is theta. Okay, that's what we get with our eyeballs. Now you might want to verify this rigorously, and to verify it rigorously, it's really not too hard. What you can do is draw a line, a horizontal line right there. If I do that, then what? So here's the horizontal, here's that E hat 1 direction. So therefore this angle right here has to be theta. And if that angle is theta, then this angle right here would have to be what? Remember, these two yellow vectors are 90 degrees apart, so this one would have to be 90 degrees minus theta, right? So now if we look at this triangle, this one right there, trying to draw it in green here, that's a right triangle with that right angle there. So this angle is 90 degrees minus theta, then this one has to be theta, which is exactly what we hypothesized earlier on. So I think now we're in agreement that this angle right here is indeed theta. So let me clean that up here. So that one we said was theta. So before we continue, let me just move this to the side. And now we can start doing some trigonometry, right? The piece in the E hat 1 direction was opposite of the angle theta. If W is the magnitude of that weight vector, then we can say our weight vector is W sine theta in the E hat 1 direction. And I'm happy with the sign of this, right? So this component of the weight was in the positive E hat 1 direction, right? This vector right here is in the positive E hat 1 direction. They're both going down the slope and to the right. The other piece is going to be the cosine because it's adjacent to the angle. So that I have W cosine theta, E hat 2. But notice this piece of this component of the weight is in the opposite direction as E hat 2. Therefore, I'm going to need a minus sign right there. And there's my answer. All right, so we should feel good about ourselves. But before we finish this video, I want to consider one more case. So let's suppose that we are not given theta. All right, so let's get rid of this theta right there. But instead, I was given the dimensions of this ramp. Let's say this horizontal extent here was a distance x, and the corresponding vertical rise or fall over that distance x was y. Right? So instead of being given theta, we are given x and y. How would we decompose these vectors w, f, and n? In this case, again, we're going to keep the E hat 1 and E hat 2, but we don't have theta anymore. All right? Well, first of all, n and f are easy because they're the same. So n and f are perpendicular and parallel to the ramp. E hat 2 and E hat 1 are perpendicular and parallel to the ramp, respectively. So those are still just as easy as before. But when we wrote the weight, we cannot use theta, right? Because we're not given theta. I guess we can find theta, right? If we took the tangent of y divided by x, that would give us theta. So, but then our answer would be in terms of the sine of an arctangent of y over x and a cosine of an arctangent. And that just looks messy. I don't want sines and or cosines of arctangents. I want to write this thing more cleanly in terms of the x and the y. And the way we do this is actually quite simple, and you should get familiar how to do this sort of thing. Now the definition of sine, this function we have in here, is as follows. Sine of this angle is just the opposite side of the triangle, the y, divided by the length of this hypotenuse. So that's y divided by, what's that hypotenuse? Using Pythagorean theorem, that's x squared plus y squared, the square root. Fit that in. And similarly, the cosine, maybe I can make this one look a little neater. Cosine is going to be the adjacent side divided by the hypotenuse. So the adjacent side would be x, and the hypotenuse again, x squared plus y squared, square root, fit it in just perfectly there. Okay, so what we need to do is make those substitutions into our expressions above, and then we're good. So this horizontal component is going to be w times y over x squared plus y squared, square root, and that's the E hat 1 component. For the E hat 2 component, I've got a w, and now I want to use the cosine. That would be x over x squared plus y squared, square root. That's in the E hat 2 direction. Get it? But again, I got to be careful because this component of the weight is actually in the minus E hat 2 direction. So I got to put a minus sign there. And that's it. In fact, before we accept this as our answer, maybe we should do a little thought experiment to just check things out. What happens if I keep x the same, don't change that one, but we're to make y get smaller, right? Keep x the same, let y get smaller. That means the ramp would get more shallow, right? Become less steep. If the ramp becomes less steep, then what happens is the E hat 2 becomes more vertical, and all the w would be in the minus E hat 2 direction. So let's look at this. If I let y get really small, that means the E hat 1 component would go away. That's exactly what's supposed to happen. And all of it would be in the E hat 2 direction, right? If y gets really small, then this term looks like x over x, which is just 1, which you just leave the weight. So that looks good. So if I let x get really small and keep the y, that would mean make this thing really, really steep. In that case, all the weight would be in the E hat 1 direction. In fact, that's exactly what happens in this. So I'm thinking this looks quite good. I'm comfortable putting a box around it and saying that's our answer. All right, good luck with this.